These are Chapter 14 problems. The first one we're going to look at is number 19, where we will predict the products that are expected when each of these is heated with concentrated HBr. So we have excess HBr. And the first thing that's going to happen here is we're going to get a proton transfer. So that becomes protonated. And the only thing that we can do in this case, we have Br- to act as a nucleophile. And the nucleophile can attack here because we're doing an SN2 reaction. Which would leave the alcohol plus CH3 Br. We're not going to see an attack of here because that is an sp2. So we'll only see the CH3 Br and then phenol. In this reaction down here, we can get attack on both sides because this is secondary. So we'll see a Br here for the first half and also the Br for the second half. So you can write both of these or just two bromopropanes. Two bromopropanes. All right, and this is a similar problem. No, this is a different problem. We're starting with cyclohexene. And we need to synthesize this compound using any other reagents. So what I'm recognizing here is that this is an ether on one carbon. So one way that I could do this is to use cyclohexene, mercuric acetate, and then just use T-butanol with sodium borohydride. So that will get me to my target molecule. Another thing that you can do from cyclohexene is I can make it an alcohol. Actually, I can make it I add HBr to make it a Br, and I'll show you in a minute why I don't want to do it the other way. So once I have that alcohol, I can take tertiary butanol and use sodium hydride and add this Br to it. And that OH can attack that Br to get the tert butanol here. What I don't want to do, so I started to add water. And if I was trying to carry this step on, I would use NH and this tertiary butanol, but I would be trying to do an SN2 attack on a tertiary center, and we can't do that. So this does not work. No SN2 at tertiary. So that's why I'd have to go with that second route there. Okay, so to do the mechanism for this tetrahydrofuran formed with butane diol, we're going to do a couple of proton transfers, and because we're making a cyclic structure, this is going to be an intramolecular reaction. All right, so the first thing we're going to do is one of our alcohols is nucleophilic, and that's going to grab a proton. So our first arrow is a proton transfer. Oxygen picks up a proton, and now it's positively charged because it's lost one of its lone pairs. Now the other alcohol that is in the system is going to react quickly because it is in proximity to the other one, and that one's going to act as a nucleophile, and it's going to attack this electrophilic carbon right there. So this is our electrophile, this is our leaving group nucleophile. So we're going to get a nucleophilic attack, and that leaving group is going to leave. So there's two arrows there. And if I count my carbons, that's the one doing the attacking. I have an oxygen here, and then carbon 1, 2, 3, and then there was 4. And then there was a new bond between the oxygen to carbon. Right there. And then this oxygen on that alcohol is still there. And there's a positive charge here. And then to get to tetrahydrofuran, we just have a proton transfer where an H2SO or HSO4 minus can grab that proton and give oxygen back its electron. So that's how you would do that mechanism. All right, for identifying reagents here, we just want to look at the next step and see what is happening. Between acetylene and the next step here, we're adding one methyl group. So we need to have a base to make the minus charge there, so NaNH2. We're adding one carbon, so it's CH3Br. And in the next step, we're adding a carbon to the other side. So we're just going to do that same step again to the other side. And then to go to C, we're going from an alkyne to an E alkene. So we need to go through the radical mechanism, or sodium with liquid ammonia. And then for D, we're just making an epoxide here. To do it in one step, we can use MCPBA. And then for E, we're doing the Z alkene. So this is H2 with Lindlar. And we want to make sure to use Lindlar, which will stop at the double bond. If we use H2 regular, then that would go all the way to the alkane, which we don't want. And here we can use that same reagent, MCPBA, to make the epoxide. All right, here we're predicting products. The RCO3H is that reagent, just like MCPBA, that will make my epoxide. And NAS methyl is going to attack at the less substituted side. So I'll get an OH here, add the SME here, and that water is just part of the workup. For this second reagent here, E, we're going to make a Grignard first, which can then attack the epoxide, followed by water. And this is symmetric epoxide, so we don't have to worry about what side that's on. But my OH will be furthest away because that's where the bond is breaking. Right here, a plausible mechanism. I have a nucleophile here. This is my electrophile. Because it's negative, it's going to attack on the less substituted side to get this product here. So we've just added those two. And then for this one, we're going to do a protonation first, or a proton transfer. And then as that bond weakens, this can attack here. And we get that S-methyl addition there. All right, for missing reagents here, if I start in, I'll start up here with that cyclohexene. To get the epoxide, I can add MCPBA. For an epoxide where I'm adding this group right here, I can use a Grignard, so that would be this Grignard. And on this one here, we're doing an attack at the more substituted, so I'm going to use methanol with H+. If I go down from that, I'm making another ether. So here I can use sodium hydride and add CH3Br. I'm going to go back into the center here. I have this epoxide. We're adding this S-methyl to the less substituted side, so this would be NaSMe. If I want to add just an H here, I'll use lithium aluminum hydride. To add a Cn to the less substituted side, I use NaCN. Here I'm adding Br to the more substituted side, so I just have HBr here. And then going left from the epoxide, I'm adding OET to the less substituted. And then this would be a similar, we're making an ether from the other alcohol, so it'd be NaH. And then ethyl bromide. All right, number 35, we're looking to fill in the missing products below. If I start with the cyclohexene and go to the mercuric acetate, my product here is going to be an alcohol. Actually, it'll be an ether because I have an OET behind there. If it was water, then I would get an alcohol, but since there's an alcohol there, we're getting an ether. And if your alkene was asymmetric, then the ether would go to the more substituted side. If we add excess hydrogen iodide, that is going to react with both sides. We'll end up with iodine here and also ethyl iodide. So you get two products there. For cyclohexene plus a peroxy acid, this will give us an epoxide. If we react that epoxide with C or acetylide, that's going to attack one side. We're going to make an OH over there. And then we'll have a C, triple bond C there. If we have sodium ethoxide, that's going to attack one side. We get an OH. On the opposite face will be S plus the ethyl group. And then with HBr, we'll get OH on one side and Br on the other. So in this one, this would be nucleophilic. So if you were asymmetric, this would go to the less substituted side or attacked at the less substituted. This is nucleophilic, so it would go to the less substituted side. HBr is neutral, so that would add to the more substituted. And that's what would happen if you had an asymmetric group here. So let's say there was a methyl group here. That's what you would see there. A synthesis here. I have 3 carbons. I'm adding 3. And also another chlorine at the secondary position. So this is the group that I'm adding here. I can think of that group as coming from here, plus the Grignard, and this group may have come from this epoxide. So if I add magnesium, I make the Grignard. And then here I'm going to add this epoxide. Which will attack here at the less substituted position. and I have that carbon on the end. And then just to switch to the Cl, I can now add just zinc chloride and HCl. For this synthesis, I'm looking at forming an ether. So this one can be done in one step. NaH. I'm just adding this ethyl group. So ethyl bromide or bromoethane. And here I'm adding 1, 2, 3, 4. This ether. This one can also be done in one step. Nope, it can't. Because that's adding to the end. So I need to go to this alcohol here, which I can get from the alkene. So I need to use BH3. And then I can do NaH and bromoethane. And that should get you to that problem.